Hey guys, so today's video has been kind of a long time coming. I've kind of went with a very deep dive on this topic, and I figured that I would do the justice of letting you guys have a deep dive if you so choose. If you don't, you can just kind of see the demonstration in the beginning and be on your way. But for those of you that are interested in how this actually works and all of the cool tricks that I used, as well as some interesting math properties that I use that are useful for other things. Stick around. I will be covering everything very in depth today. This is probably going to be one of my longest videos that are slightly tutorial based yet. And it is covering a topic that's pretty specialized, but pretty specific to me. But what this is a circuit solver in Minecraft. So that means it can figure out the voltage and current at every element for voltage sources, resistors, and current sources. And it also calculates the power of every element. So what this means is I can flip this around, do some trigger setElem set 250. Now it's 2.5 milliamps, and I can run function ck solve, and it'll give me new values for the voltage at each of these nodes. So we have minus 5 volts because the voltage source is backwards with respect to ground, and then it drops down to 1.6, and it calculates all of the different things, such as the voltage drop across this element, which is 5 because you drop from here to here, and as well as the current in here, and the current here, and the current here and here. So let's go ahead and flip these back around and set this back to 1.00 milliamps and go ahead and run it because that's what I use for my examples here. So there we go. We have all the values again. You'll see that it's not 100% perfect. There is some flaws, but that's because there's numerical diffusion because Minecraft does not work with decimal points too well. And there's a lot of places where error kind of accumulates, and we'll see that during the presentation. So yeah, we have all these. Do not worry if you are not familiar with how circuits work. I'll be covering everything from the very basics all the way up to the very complicated. So no matter what level you are in terms of knowing how circuits work, there is going to be something new here to learn for everybody. Anyways, so let's get right into it. So a lot of this is going to be inside of a presentation, which the presentation you can download in the description in case I go too fast or you want to take a look at each individual slide. There's also a link here to the Fallstad, which is a link that if you put in your URL, it will pull up this, which is a simulator page, so you can take a look at all of the different examples. We have of circuits, and you can see kind of the voltages in the bottom right and the current at each of these points just to see what it's supposed to be. So this is a real circuit simulator and solver. So yeah, you can follow along with that if you want, but we're going to be using the examples from there. So first off is the circuit basics. So this is for people that don't know what circuits are, how electricity works. So you have three things when you have a circuit. You have voltage, current, and resistance or impedance. In this case, we're only focusing on resistance, but impedance is kind of like a overall term for all types of things that change the flow of current in a circuit. So voltage is going to be the difference in the charge between 2 points. So if you have point A, which has some measurement of its potential, and point B, which has some other measurement of its potential, then your voltage is going to be the potential at A minus the potential at B. The second thing is current. So current is the rate of flow of charge of electrons. It's how many electrons are flowing through a certain point at any given time and what direction. So this one needs to have some kind of arrow associated to note the direction. But a lot of times the direction is kind of negligible for the questions that you may have about a circuit. Anyways, then the last one is resistance. And this little picture cartoon on the left is very commonly shown for the three relationship. So resistance is making it harder for current to go through, and voltage is trying to push the current through. So yeah, when you have some kind of a resistor, you're going to have the voltage, which is going to measure essentially how much it wants to send stuff that direction, and the current is how much of that is flown that direction. And then power is just energy consumption. It's the voltage times the current. So kind of a good way to think of this, if you don't know already, is to compare it to water. So let's say you have 2 tanks of water that have the same amount of water in it. So that would mean the same amount of voltage because they have the same amount of potential. They have the same amount of possible potential energy. They could go from they're going from the same high energy state to low energy state. But the difference is the pipes are thinner on the one on the right, and the one on the left, they are thicker. So the one with the thicker is going to have less resistance, which means that the flow is reduced less, which means that you're going to get more flow. Okay, so the relationship between these three, as we showed before, is the current is the voltage divided by the resistance. So if you have the same potential, but the resistance is higher, you're going to get less flow rate. And that's why it's kind of compared to water. Let's just ignore all kind of force equals pressure times area, pressure equals force equals pressure times area stuff. Let's ignore those kind of laws. But it's very similar to water flow. So when you have something in series and resistance, the total resistance is some kind of a sum of the parts. You can think of this as, if you want to relate it to water, you can think of this as you have a pipe and the pipe gets smaller and smaller. So what is the overall flow that will be through the pipe is just going to be a sum of all of them, all of your resistances. So you have to, with the equivalent resistance looking from here to here is just the sum of all of them. Now, when you have a split or parallel resistors, that means that the flow could go in one direction, the other direction, the other direction, or the other direction. So there is 4 different directions that the flow could go, and the flow of electrons will want to go to the path of least resistance, but it will go to the other paths just proportionally to how less the resistance is there, unless you have a short. So the overall total resistance from A to B, what you can kind of equivocate this to, is 1 over R1 plus 1 over R2 plus 1 over R3 plus 1 over R4 equals 1 over RAB. So this is just a formula which shows you kind of how to combine these to get some equivalent result. What this actually also means is that if you have resistors in parallel, their overall resistance is going to be less than any of the individual resistances. So let's say all of these were 5, best case scenario. The overall resistance is going to be 5 over 4. I think so. Let me think. 1 over 5, 1 over 5. Yeah, 5 over 4. So yeah, when you have kind of a split, your overall resistance is always going to be less than any of the individual resistances. Okay, so that kind of gives us circuits basics. So how to combine resistors, how to calculate how much voltage you have based on the current and the resistance, or how much current you have based on the voltage and resistance, or how much resistance you have based on the voltage and the current. Now we get to how to actually solve a circuit. So let's say you have like a complicated network of resistors and capacitors. Well, not capacitors, resistors and voltage sources and current sources. So there's 2 methods. There's Kirchhoff's laws. These are KCL and KVL. So Kirchhoff's current law basically states that any current going into a junction has to sum up to 0, or all the currents entering have to equal all the currents leaving. This makes sense. Let's say you have like this junction, right? Or let's just say you have this corner here, right? You have to assume that the current going this way has to equal the current exiting. Otherwise, you're going to have current like magically storing up inside of it, and now you have current in a point and it's not flowing, and what is going on, right? That doesn't make sense. So you have a flow, so it has to flow. So some of it has to be it has to have as much flowing into it as flowing out of it on the same wire. Then, of course, you have Kirchhoff's voltage law, which basically states that when you go around a circuit in a circle, kind of clockwise, doesn't matter. If you add up all of the voltage drops, so this is a potential, minus to plus, you can calculate the potential. Plus to minus, you can calculate the potential, plus to minus, and all of your voltages have to, all your drops have to equal all your rises. So if we're going in a circle that is clockwise, the source is a rise, but since we see the plus and then a minus, each of these individual components are drops, which makes sense. A resistor is going to reduce the voltage anytime you see a resistor. It's going to make the voltage go down until you eventually reach the negative terminal, which would mean you're at 0 volts assumed, or at least 0 volts with respect to the battery. So KVL is not very useful for us because when you're writing a computer program, KVL can be a little bit confusing or difficult to do because you have to first define what is a loop and what is a unique loop, and that can be kind of tricky. But KCL is actually more interesting because these junctions are actually definable, especially with finite elements. Like you have a resistor, well, it has 2 points at the end points, so there could be a junction at either end. You just have to find a way to reduce how many junctions you're calculating. So we're going to do a KCL example, and we're going to solve it using kind of like the math way. So the first step is to mark all of your nodes. So these are our nodes. Nodes are unique areas of connection. So they're basically just unique junctions. So this wire here, up here, is a unique junction between the resistor and the voltage in the current source. This junction down here is a unique connection between the resistors and the ground. And this junction right here is a unique connection between 3 resistors. Then you have to remove the nodes that are connected to ground because they're going to have 0 volts. Why calculate them? Then you have to find basically the sum of all the currents going in to the node and say they're equal to 0. So the current going into node 1, well, we know that node 1 has to already be 5 volts because it has a voltage source connected to it, so we might as well not do an equation for node 1, but let's do an equation for node 2. So there's 3 currents going into node 2. There's current flowing from node 1 to node 2. So to calculate that current, we go the voltage of node 1 minus the voltage of node 2 divided by the resistance, because V over R is equal to I. But it's it's not just V as a plain number, it's VA minus VB. So V at the voltage at node 1 minus the voltage at node 2 divided by the R is going to be our current pointing inwards. And likewise, the voltage at node 3, aka the ground, voltage of the ground, minus the voltage at node 2 gives us an arrow pointing towards you, divided by 1,000. So to know which one goes on the left or right side of the minus sign, the one on the left side of the minus side is where the tail end of the arrow for the current would be, and the one that goes on the right side of the minus sign, the one that is subtracted, is whatever your node 2 is, because you want it to be going into node 2 and say that all of these currents equal 0. So then if you substitute the 5 volts in, and then you end up with 5 minus voltage at node 2 over 1,000, plus 0 minus voltage in node 2 over 1,000 plus 0 minus voltage in node 2 over 1,000 equals 0. So if you sum all these guys up, you end up with 3 of the voltage node 2 over 1,000 plus minus 5 over the voltage node of 1,000. And then you can move it to the other side, and then you can cancel out the negatives, and you end up with the voltage in node 2 is 5 over 3. So this actually is going to follow a similar pattern that we can kind of extract some kind of an algorithm from. So how can we do these math steps algorithmically? So one of the ways is to use matrix math. So computers are great at handling matrices. Minecraft not so much, but we'll get to how to deal with that. But there is a very nice way to solve a system of unknowns, which the unknowns being the voltages, for the using the resistors as inputs and the voltage and the current. To do this, you have to construct a matrix A, which has all of your coefficients, and then the matrix A times your matrix X, which is all your unknowns, is equal to your matrix Z, which is all of your right-hand side, which is all of your results. In this case, there's going to be a lot of zeros, obviously, because for the nodes, our Z's would have to probably be either 0 or whatever voltage is connected to them. In this case, your Z would be like 5 over 1,000, and your X would be voltage in node 2, and your A would be 3 over 1,000, right? So this can be solved by moving the A to the other side, and taking the inverse of A times Z will give you all of your answers of X that you're looking for. So now we just have to come up with a way to find this A matrix and the Z matrix, and then do the math, and you'll get X. So to do this, you use MNA, which is modified nodal analysis. This is just one method for solving circuits that works with voltage sources, current sources, dependent voltage sources, and dependent current sources, I think, as well as not just resistors, but capacitors and inductors, but we're just using it for resistors. So what you have to do is you have to construct an A matrix. The A matrix is going to be n plus m by n plus m sized, and it will have 4 components, G, B, C, and D, that make it up. The size is how many nodes you have plus how many voltage sources you have, and then that is your 2D matrix size. So when we're solving for G, so G is going to be probably the most complicated matrix that we have to do here. It is n by n sized, so it's however many nodes you have by however many nodes you have. In this case, we have 2 nodes, so it's 2 by 2. So what you do is in the ith and jth elements, if it's a diagonal, which means I equals j, okay, so I is equal to the node you're at, j is equal to a node you're looking at, and you have to look at the resistances connected between those 2 nodes. But if you're on I and j is equal to the same, then you're just at your own node. So when I and j is equal to 1, then our node, what we need to put in for the matrix is the total equivalent resistance. And this resistance will be technically in parallel. So we put 1 over 1,000. Then when you're looking at just node 2, you need to have the sum of the 3 parallel resistors. So 1 over 1,000 plus 1 over 1,000 plus 1 over 1,000. And that's what goes here. And you can see that right here. And then in the ones that are not the diagonal, so you're going to have a lot of non-diagonals, you have to go from one of the nodes to the other node and calculate the resistance between them, multiply it by -1. So in this case, we go to node, so our I value is 1, our j value is 2, so we go to 1, we look at 2. What is the resistance between them? It's just 1, so 1 over 1,000 times -1. And the inverse will also be true. So we're going to have kind of a mirroring about the diagonal in this case, which then leaves you with 1, -1, -1, and 3 simplified, and times, it should be divided by 1,000. So that's how we get the G matrix. It can be kind of complicated. Now let's go to the B matrix. The B matrix is a lot easier. You go to each node, and for each, it's going to be a node by voltage source. So the horizontal width is going to have to do with how many sources you have. The vertical is going to be how many nodes you have. So wherever you are on the vertical, that's what nodes you're at, and then whatever you're at the horizontal. So the ith element is going to be what voltage source you're looking for. So for the first element, we go to the first node and we look for the first voltage source. So we go here, we look for the first voltage source. Oh, it's connected. If we are at the positive terminal of the battery, then you put a +1. If you're at the negative terminal, you put a -1. If you don't have a terminal, so we go to voltage node 2, we look for voltage source 1, and it's not connected because there's a resistor between us, so it doesn't count. So then we put a 0. And this will basically help us figure out where we're going to put the equals 5 over 3, right, in the formula. So then the C matrix is just a transpose of the D matrix, and then of the B matrix, and the D matrix is a voltage source by voltage source sized thing, and it has a 0. It's used for dependent voltage source calculations. You would put I think you would put a 1 or however much the formula is in that equation. But in this case, we have no dependent voltage sources, so it's always 0. So then creating the X and Z matrix, this is the last step. So the X is going to be where your answers end up. The Z is going to be kind of like your source dependent things. So the X matrix is going to be, they're both going to be column matrices of size n plus m, which is going to be nodes plus voltage sources. The X matrix is your answers. So the answers this thing gives you is your voltage at node 1, your voltage at node 2, and your current through the voltage source, or all the voltage sources, if you have more. Then your Z matrix is going to give you is going to be the sum of all the currents going into that node for the first for all your nodes, and then you add at the bottom all of your voltage sources that correspond to where you put the voltage sources in X. So if you had 2, you would want the order for X to be the same order as Z. The current going into node 1, you have an arrow pointing towards you, so that is 1 milliamp into node 1. Not it would not be if it was pointing away, it would be -1. Then at 2, you have no current sources pointing into you, so you have nothing, so 0. And then lastly, the voltage source is just 5. So you just put 5. If you had another voltage source, you put 3 under here, and so on. So then to get the solution, you have this, and by this matrix constructed by putting everything together, G, C, B, and D, multiply it by your Z, take the inverse, and you get this as your answer. So it says that 5 volts go to node 1, 1.667, which is 5 over 3, goes to node 2. And we have minus 2.33 milliamps, which goes to the 5 volt source. What this means with the negative means that the current is pointing into the negative terminal, out of the plus terminal. That's just sign convention. So that means that the current is pointing upwards here, the same way that this current is pointing. Okay, so that is how to do multi-nodal analysis. We're going to come into the question of how do we do it in Minecraft. That's the real kind of interesting part here, but I had to give a bunch of that background so you know kind of what we're trying to do, what our thought process is, what we're trying to get at. So first off, what do we need and what can we do for it? So decimal point math, we don't have it. So what are we going to do? We're going to use scaled integers. So 1.00 is equal to 100. And we just have to make sure that we do proper multiplication and division of tens places so that all of the zeros don't kind of accumulate and keep getting bigger. And you're all of a sudden like, why do I have like 100 million, right? So you have to kind of keep track of that. Then you also have arrays. So we can't do arrays, and that's going to be really tricky to us, no array math. So we're going to use data storage. And data storage is going to help us with the not using integers thing, because we can scale things to a double and scale it down when we store it onto the array, and then pull it off of the array and scale it up however much we want. So that's really nice. Then we have inverse arrays. So inverse arrays, so inverse of an array is very tricky on its own, and we're gonna have to do some kind of algorithm. Multiplication of an array, some kind of algorithm. Continuity detection, so detecting if a loop is closed. You can use block check recursion, and we'll go over all these things later. Node detection, we're gonna have to use block check recursion with stops, and you'll see what I mean by that. Nodal resistance, that is the resistance at each node. You can use scoreboard ID linkage of components. So each component is linked to a node, or a node is linked to each component, and you can figure out the total by finding all of the linked components. And then node to node resistance uses bi-linked scoreboard IDs, which means that you have multiple scoreboards which have the same number for associated linkage. So you can basically find A to B because A is one of the nodes and B is one of the other nodes. And we'll go over these all in detail. So first off, recursive fundamentals. So how do you kind of do recursion, and what kind of recursion we really like here. For this algorithm, since we are creating, and I'm going to pop into Minecraft here just to demonstrate what's going on. Let's go ahead and grab some circuit elements. Okay, so we'll come down here. So let's say we have some kind of a loop, and maybe the loop isn't closed. Okay, so how are we going to run the check and see if it works? Okay, so I can actually just run ck create, and you will see that nothing happens. But when it closes, all of a sudden now I have everything load up. Great. Of course, you wouldn't want to have no resistor, but that's beside the point. So how do we detect that this is a closed loop? So the method is using some commands, and I'm basically just going to show you guys just relevant commands, but there is hundreds of more commands that are kind of like in between handlers, but these are the important stuff. So how we kind of go, what we want to do here is we want to go to each block, and we only want to go to each block once, and we want to run a check at each block. So how do we do that? So we start by setting the block above where you're at to glass. You could use entities, which would be laggier, but in this case, since I can get away with placing blocks, I'm going to do it. So I'm going to set the block above to glass where I'm at. So let's say we start here. We're going to put glass up there. Then we're going to look in 4 directions around me. So positive x, positive z, positive x, negative x. And we're going to see if there is a circuit block there. So a circuit block would be any of these stained glass. So if we're here, we look forward. Yes, there is a stained glass. That scary noise scared me up. So there is a stained glass here. So since there is, then we're going to check if there is a glass above it. There, in this case, in the first iteration, there wouldn't be a glass above it. So we would go ahead and play ourselves again. And then when we play ourselves again, we would be here. We would place the glass and move on. So what this basically does is it moves around the grid as long as it's connected in the 4 cardinal directions, and it will just kind of loop itself until everywhere, and it'll just keep going. It'll just keep looping itself everywhere. But any commands in the red here do not play until after all of the looping and of itself has finished. So once you're in the red, you can assume that everything happening in the red is playing everywhere in your circuit at once. So this set block 1 of air is actually happening at all of these. It's going to happen, well, it's not all at once, but it's going to be sequential. So for example, we aren't going to set this block, when I run set block air in this section down here, it's not going to set this block to air and then all of a sudden one of these other loops will trip up, because this is going to be halted essentially in the recursion. This is going to happen later in the recursion because of all the looping. It's going to happen at the end of all the looping, but it will happen at every single one of these blocks, kind of like one after the other. So all of this looping is going to happen, and then it's going to be set block air, set block ice, set block air, set block air, set block air, and it's going to basically do all of them in the order that it got to those points, which is arbitrary. So we don't really know the order it got to these points. It's going to be based off of the order that I have these 4 commands in, but you will know that there will be some kind of order, and it will chain react. So this is kind of like a flood fill algorithm. It essentially says, go one thing, keep going, and select all of our elements, and then recursively update all of them at once. And I'm just going to refer to this as the flood fill algorithm from here on. So what this allows us to do is go to every block that is connected. That's cool. So how can we detect if it's a dead end? So at every block that is connected, we're going to run these 4 commands. What these 4 commands do is they check the blocks around it and see if they are not circuit blocks. So if I am at here, there is a circuit block to my right, a circuit block below me, but to my left there is air, and above me there is air. So since there's 2 non-circuit blocks, so our freedom, quote unquote, or dimensional freedom is 2. Now, if there is a block which has 3, then you can say that is a dead end. And what I use in this method is, since there is a dead end, it could be an open loop. The only problem here is that an open loop implies there's a dead end, but a dead end does not imply there is an open loop. But in this case, I just say a dead end implies that it's probably an open loop, so we're just going to not allow it to run at all. And you can see where that comes into play. If I have a closed loop, I run it, and then I have kind of like a thing jumping off there, and all of a sudden it doesn't allow it to work. There is the exception of grounds, so if it sees a ground, then it does not count as in terms of figuring out if it's an open loop. So it basically ignores the ground block. Okay, so that's how we detect if there is an open loop. So next, we're going to assume that if it is a closed loop, what are we going to do? So what are we going to do? We're going to go back through the circuit, through the flood fill algorithm again, and we're going to summon whatever entities we want at the circuit elements and set their default values. Also for voltage and current, we basically want to have a hierarchy of direction. So north, south, east, northwest, southeast is my hierarchy. So if there is a block above, then it will latch onto that and it will have whatever score 0, 1, 2, or 3. We just need some default direction. And I also assume that you're not going to do something like this. This might confuse the program. But it's not even really possible. I guess if you did that, it would be possible. But I really would suggest you don't do this because it might confuse certain things. But yeah, so you can rotate the direction later. So it kind of like assumes a default direction, but you can change it. Okay. So yeah, you do need a direction though for the voltage, so it knows what side's the plus, what side's the minus, and also for the current to see what direction it's pointing. Okay, so now we come to the final step, which is doing multi-nodal analysis. Okay, so, well, not the final step, this is second to last. Doing multi-nodal analysis in Minecraft. How are we going to accomplish this? Because we have entities, which is kind of like object-oriented programming, and we also have, and that's really it, and we have scoreboards. So how do we do this? So first we have to find the nodes, right? That's our first step in M&A. Multi-nodal analysis, find the nodes. So how do we find the nodes? So this algorithm that I have written on the right, and I'm going to go through all of the steps and it will animate for you guys. This is how we do it in Minecraft. So we go to every element, and we are going to assume, because in a nicely put together circuit, each element will only have two connections, right? Obviously you can place glass blocks such that they have 3 connections, but you're not supposed to do that. And I'm going to just assume you didn't do that for the case of the multi-nodal analysis. So we're going to go to every circuit element and spawn a node marker at either side. So we basically spawn an entity at either side. There should only be 2 sides to every element. Okay, so then we're going to enumerate them all, and we're going to link their IDs with the thing that they're connected to, or the element they came from. So we're going to count 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this voltage element is associated with nodes 0 and 1. This one is associated with nodes 2 and 3. This one's associated with nodes 4 and 5. This one's associated with nodes 7 and 6. And this one's associated with nodes 8 and 9. And the way we do that is we have 3 scoreboards, node ID. Node ID is going to count 0, 1, 2, 3, 4, 5. It's going to go to every node and count 0, 1, 2, 3, 4, 5. You just do that by doing execute as at e tag equals node. You go to all the nodes. You run a function. The function adds 1 to a global counter and moves the global counter onto the scoreboard of that entity. So what that'll essentially do is count up. Then as for the node IDs, then you're basically going to go to the parent, which you already know, and you're going to connect the nodes to them. So node ID A and node ID B is the scoreboards that the element is going to have. So node ID A is 0 here, and node ID B is score of 1 here. The order doesn't matter. So sometimes node ID B is below and A is above, and A is below and B is above, and that's going to kind of come back at us later, and we'll see. But there's ways to handle that. But yeah, this assumes that all elements should only be connected to one node on either side of them. There shouldn't be kind of like a resistor with 3 connections. So then the next step is we have to eliminate these because we have way too many nodes, right? So what we're going to do is we're going to go to every node, look for another node that's connected to them. So in this case, we start at 0. We basically use the flood fill algorithm to look for other nodes in the path disregarding circuit elements. So the flood fill algorithm goes around just on the wire and ignores the other blocks. So we start at 0 and we go around and we find a 6. If it finds another node, kill the originator, stop the flood fill algorithm, and reassociate this new node's ID with anything that has the original killed node's ID. Okay. And so what this basically means is we go to 0, we find a 6, we delete the 0, and we change where it says 0 here to 6. So if we follow this algorithm, we go to 1, we find a 2, so update the 1 to a 2 on the voltage source. The 2 finds a 4, and then the 4 gets updated. 3 finds a 7, update the 3. Then 4 finds a 9, so we have to update 3 different elements IDs. Then 5 finds a 7, then 6 finds an 8, and 7 cannot find anything, and 8 cannot find anything, and then 9 finds a ground. So a ground is also a means of deletion. So 9 finds a ground, and then it decides, hey, we're all ground. Technically, in the process, 4 could have found the ground. Just depends on the order of the flood fill. If going to the right is higher in your hierarchy, then it'll go to the right first. But it'll still either way end up in that. So then the final step is to renumerate all the nodes because these 7, 8, 9 are their arbitrary numbers. Now we renumerate them to 0 and 1. So we go to all the 7s that are on the node IDAs and update them to the new value of 0, and we set that node's value to 0. So now we have a circuit where we have node 0, node 1, and then we have node IDA saying 1 and node IDB saying ground, some number associated with ground. In my case, -1, but it doesn't fit in the box good. So yeah, this one's connected to 1 and ground as well. This one's connected to 0 and ground, 0 and ground, 1 and 0. Perfect. So that actually creates our nodes. Now we basically have to build the G, B, C, and D matrix. So how do we do that? So we have recursive matrix building. So let's kind of like break into this. This is another form of recursion. It's not physical. It's just scoreboard recursion essentially. So what we do is we have something and we have some I and J score, and we basically append a value in. This is basically an I loop. This is like, you can think of this as double for loops. So here's your I and here's your J. So in the I loop, we're going to append a row. This adds a row to some matrix, and then we're going to run J. What J does is it appends a value at the last row. So it goes to the bottom row, G at -1, that means last, and it appends a 0 to the end of the row, okay? And then you're going to do stuff to that. So you're going to go to the last row, you're going to go to the last element in the row, and you're going to store some number on there. Then you're going to increment J. So this will basically, for all, whatever your max number is, it will basically fill out the horizontal part of your array, and this one will fill out the vertical part of your array. And this basically lets you path through an array going horizontal first and then vertical second, and it builds an n by n array. Or you could do n by m. It doesn't have to be 2D. It could be any size. You could have different values for max, J, and I. So then how do we build the G matrix with this? Well, those were already some commands for the G matrix, but the important part, anytime I refer to kind of like an IJ operation, I'm mainly going to be showing stuff either happening in the I or happening in the J part. And what that just means is stuff happening at the row level or stuff happening at the individual element level. So at the individual element level, there are three things that happen to get the G matrix. So we have to accumulate the diagonals. Okay, so how we accumulate diagonals is actually really easy. So we go to every resistor that we're operating on, and we check if their node ID A is equal to the target node ID, which would be I or J. And then we run cumulative res function. And the cumulative res function sets a value to 10,000, divides by whatever value the circuit is. So let's say that the resistor is 1,000 ohms, which is 1.00 kilo ohms, which is 100 in Minecraft. So it's 1.00 kilo ohms, and we just translate that as 100. The reason I chose to do 100 equals 1,000, 100 equals 1, which equals 1,000, is because in typical circuits you work with kilo ohms and milliamps. So I just wanted to use kilo ohms and milliamps as a display, but really we're just doing singular units, so 1 and 1. So 10,000 divided by 100 gives you 100, so that'll give you 2 decimals of precision on that division with truncation. And then you add that to the cumulative term. So the cumulative term starts out at 0, and then if you find one, it'll be 100, and if you find another, it'll be 200, and if you find another, it'll be 300, which is 3.00, which is what we want for that node. And then so that's how you basically do the diagonal. Then to do the from A to B, that one you have to go to all resistors, check if their node ID A is equal to I and their node ID B is equal to J, or if their node ID B is equal to I and their node ID J is equal to A. So this kind of has to do with they could be flipped order because we didn't really care. Then you accumulate their resistance again. So you add this kind of fraction thing. And then you multiply it by -1 because we need the negative sign. So that builds the G matrix. That's just very mathy way, but basically it works off of the fact that we have the associated nodes here like this. We can do it without much recursion. You just need recursion to build the array. Okay, so then we have the B matrix. B matrix is actually a lot more complicated, at least in the commands, but less complicated in the process. So the way the B matrix works, we need a new algorithm here. So we need to numerate all the voltages. So we need to give the voltages some count. So if we had 2, we would have 0 and a 1. All right. So then we have to go to node I when we're building this IJ array, and we have to search for voltage source J. So we load some ID, which is the ID we're looking for, and we load some node, and we go to some node, which is the node we're starting at, which is I. And we go along the path, canceling out at any of the elements. So we stop when we see an element, and we look at connected elements and to see if there is a voltage source there. So if there is a connected voltage source, no, it's a connected resistor. Is there a connected voltage source? No, it's a connected resistor. Is there a connected voltage source? No, it's a connected resistor. Okay, well, if we find one, so at this one, we see, is there a connected voltage source? Nope. We go around this path. Is there a connected voltage source? Yes, there is. Okay, so now that there is, we need to look at the scoreboard that we set originally for the direction, so circuit direction, and compare, like, where did we come from? Where did we go? Where did we come from? So we came from north and we went into south. So we went into south, and what is the value of the direction? Well, if the direction is directly opposite of where we came from, then it's +1. If it's the other way around, then it's -1. And otherwise, it should just be 0. So you can kind of work this out based off of where you came from versus what the scoreboard value is, and you can figure out whether to put a +1 or a 0 or a -1. In this case, it's a +1 because the circuit direction was, say, 3, and we came from +1. So yeah, I found 1 going into it, but then 3 is set up for -1 in the x direction, and it kind of like connects. All right, so that makes our B matrix. Then the C matrix, we just need a transpose, which can be done using 2D recursion, but swapping I and J, essentially, like swapping what I and J does. Okay, it's a little bit trickier than that, but I figured that was a very easy algorithm to do. So that one was simple. I'm not like focusing on it. And then the D matrix, you just make an M by M. So you just, again, 2D matrix, except the J stuff does nothing. So it just creates zeros. So when we put all the matrices together, in Minecraft, we get 3, -1, 0, -1, 1, 1, 0, 1, 0. Okay. So to put them together, we basically just need to we have the G, the B, the C, the D. We just need to pop the values off of the G, the C, B, the C, the D onto A. So in the J stuff, we decide when to pop based off of where we are based on N. So if we go past N, then we need to start popping from B. If we're before N, we need to start popping G, because G is M by N and B is N by M plus 1. And then same with the J, so you have all this logic of whether to pop from G, B, C, or D, depending on where you are in the 2D array. And then again, depending on where you are in the array, pop a row off of G, B, C, or D. Okay, so that creates our combination array here, 3, -1, 0, -1, 1, 1, 0, 1, 0. So now we have to build the Z matrix. So that gets our A matrix. Now we need the Z matrix. So for the Z matrix, we need to go to each node and do a flood fill algorithm. And we have to accumulate all of the current pointing into it. So the same logic as checking if a voltage is pointing into it, you need to do with checking if a current is pointing into it, and then sum it. And then finally, we need to go to all the voltage sources in the order that we ID'd them earlier and put them on the list, append it to the list. So 0, 1, and 5 is our order here. So now we get to the tricky part of matrix inversion. So how are we going to do the inverse of A times Z? Well, the inverse of A is kind of defined as the adjugate of A divided by the determinant of A. Maybe you don't know what adjugate and determinant means, but what it means is a lot of matrix operations, a lot of matrix access, and it's going to be expensive. It's going to be hard to do. So we want to go for the simplest algorithm possible. So I found a paper called An Efficient and Simple Algorithm for Matrix Inversion, and it really is simple and efficient, and I implemented that in game. The link is right here to the research gate where you can download the paper if you want to read it. But it's actually pretty simple. This is the entire algorithm written in MATLAB code. But what it basically does is you iterate across. It only works for n by n arrays, but you iterate across for all of the n dimensions, right? So it's n by n, so it's 4 by 4. You do 4 iterations of this. What you do is you go to a pivot point, which is going to be one of your diagonal elements, and you grab the pivot point. Then you go to where you are, what pivot point you are, so which diagonal element you're on, and you want to edit the entire column associated with that. And you're going to update that value as the value it's at divided by the pivot point minus 1. Then you're going to go to all of the elements that are not at the pivot point. So it's going to be things that aren't on that column and row. And all those points are going to be updated based off of their value plus the pivot points column value times the pivot points row value, something like that. And then you're just going to add up that value. And then after that, you go to all of the, you go to the pivot point and you go to all the elements in the same row and you divide those elements by the pivot value. And then you go to the exact pivot point and you set that as equal to 1 over the pivot value. And if at any point the pivot point is 0, then you probably cannot invert the array, or at least by this method you can't. You can also, this D is the determinant, so you can actually calculate the determinant by this method by just doing the determinant is equal to the determinant times the pivot point. And it will kind of like create the determinant over time. So yeah, this is a cool kind of iterative approach of doing weird matrix operations. But what really is important here is that we are accessing the array we're trying to invert a lot of times. So to do that, we have to have hard code. We can't do, we have to have hard coded access, like array access, for the best efficiency. It would be tens of thousands of commands if it was not hard coded array access. So get, so we have get and set. So get basically says go to check if you're trying to get something from a specific row. So let's say if ti is 1, then we're getting something from row 1. So then run this function. And then this function says if j is 0, then grab 0, 0. If j is 1, grab 0, 1, and etc. So it goes on to however many you want to hard code. So it's kind of like a branch that branches out based on however many rows you want to support. Set is the same thing, except you're just doing a different end result command. So how do we do this matrix conversion? So we have to do the 3 different pivoting, right? The 3 different pivoting math stuff. The pivot the column, pivot the row, pivot the non-pivot row and columns. So pivot the column, we grab the element at IP, and then we invert the value. So we do the math on the value, and then we set it back. Simple. And you do that and then you iterate for all of the values of I, so that it will get the whole column. Then we do the diagonal. So you get the value at PJ, you get the value at IJ, and then you set the value at you get the value at IP, and then you set the value at IJ. And you do that. You iterate that across the whole array. So it's going to be double iteration here. You're going to have you're going to have kind of, you're going to have, this is the only iteration you actually do across the whole array. So then you have the row pivot. So the row pivot goes to all values in J of the row, same value of P, and you obtain PJ, you invert PJ, and you set PJ. So let's just assume that all works. What you should end up with is up here. So you should end up with 0.33, 0, 0.33, 0, 0, 1.00, 0.33, 1, negative 0.667. This is the perfect inversion, like the better inversion. This is using P inverse function. So what the algorithm gives us in Minecraft from the numerical diffusion is 0.32, 0.00, 0.33, so that's good, pretty good. Negative 0.01, it should be 0, 0.0 should be 0, good, 0.99, not 1.0. Okay, so that's a little different, and then 0.33, pretty good, 1.0, pretty good, negative 0.67, pretty good. All right, so to figure out kind of like error, I did something. This is not like calculating error for a 2D matrix for all of the elements is not really well defined. So I just did my own thing where I took the absolute value of their difference and then added it in both dimensions and then divided by however many dimensions we have. So I got about 0.4811% error, which is probably way lower than the real error with some nice statistical function, but I went with something simple. But you can see, yeah, there's a little bit of error we're accumulating here. We're getting a couple decimals off in the hundreds place. Yeah, so that's going to actually add up in the end. All right, so next, the final step is matrix multiplication, which is actually really simple. So you have to do the row that you're at. So you have IJ. I is going to be the row in A, and J is going to be the column in B. And then you multiply each of the elements and add them up. Lucky for us, B only has one column, so we can just use a single get filter. This is just a single, like, one function for get. And then you also need a function tree for the get from A, to get from the A. Because ours is only a Z matrix is always n plus 1 by 1, so it's just a single column, so that'll make it a little easier. So then this is kind of what we do at each element. So we use the get to get A, and then we multiply it. We use the get to get B, and then we multiply them together, divide by 100, and sum it up. And then when the sum is all added up, we go ahead and put that on to where we are. All right, so then finally the results. So the results from all this math, we got 1.65 volts at node 0. So that's right here, node 0. 4.95 volts at node 1, which is right here. And keep in mind that node 1 means everything connected to 1. And then negative 2.35 milliamps at the voltage source. So the negative meaning that the arrow is going up. Again, here's your voltage sine current convention. So what the results should have been was 1.667, 5, negative 2.33. So we are off by about 3% now. But it's really probably more than that. But again, I'm just doing a weird formula for it. But you can definitely see the error here. It should be 5 and you have you're off by 0.05, and it should be 1.667 and you're off by 2.7. So you can see, like, even with the simplest of numbers being all ones, you end up with quite a bit of error here because Minecraft non-decimals. But that's okay. So finally, we just have the power calculations. So this is how we calculate the power. It's actually a little complicated. So we have to go to each of the elements, and we know the voltage at a voltage source. We calculated the current at a voltage source, so that's the power. We know the resistance of a resistor, but we actually don't know the voltage of the resistor because that's going to be the node that it's connected to minus the other node it's connected to. And we know the current at a voltage source, at a current source, but we don't know the voltage at a voltage source, because again, that's node to node, not like you can't just say it's connected to node A, so 1, so it's 5, because node 1 is 5, because the other node could be another voltage value, because it's a voltage drop. Okay, so to do that, we just have to calculate the voltage from A to B. We just go to the node, and we go to the element, and we grab one of the you use one of the IDs of the nodes, and you grab that node's voltage value and subtract it from the other one. And then you get the absolute value, because the order is arbitrary. So I can't really give a definite sign for it, because the order of the nodes is arbitrary. The order of the node linkage. So in this case, you have 4.95 minus 1.65, because that's the two things it's connected to. So you have 3.3 volts is the drop. And then you have 1.65, because it says 1.65 minus 0, and vice versa. And that's it. So that's going to give you all your powers. You also would do the same for the current. So that was incredibly long, I'm sure. But what this means is we can solve circuits. So the simple circuit, which is a 1 volt power source with a 1 kilo ohm resistor, gives us 1 milliwatt and minus 1 milliamps, which means the current's going this way. And we can compare that with Falstad. You can see the current is moving that way in the circuit. And you can see, I put 5 volts here. That's my bad. If I put this as 1 volt, then you'll see 1 milliwatt. There you go. In the bottom right-hand corner, you see that. Okay, so then we go to the next one, and I already calculated it. So you see it puts these little nodes here, but they're kind of arbitrary. It means everything on that line. So you have 5 volts, 2.5 volts, and 6.25 connected. So 5 volts, 2.5 volts, and 6.25. And it's actually very good at calculating like the simple cases. It's when you throw in like the multiple where you have like a ton of nodes, that's where it starts to freak out. But if you just have one node, it's really good. So you have 50 milliwatts, 25, 25, 50, 25, 25. Perfect. But then you have this big case, and you can run the solve, and it takes 6,000 commands. But what you get is exactly what I showed. And you can see here we have 2.77 milliwatts versus 2.72, and then you have 10.8 versus 11.1, so they're a little bit off there by like 0.3. Yeah, and there you go. So it works for just about anything. You got to have this little ground guy connected or else it freaks out. So we can build an arbitrary circuit here. We could put one resistor here, one resistor here, and we can put one resistor here, and we can run solve. Oh, I have to run create first, and then I can run solve. And here you go. So you have 1 volt here, half a volt here, and 1 milliamp here, half a milliamp here. So then we can build the same thing here. Let's say we have this. All right, so you have, let me set this to 5 volts. So you can edit the element like that. setElem, set value 5.00, and then it'll delete all of your calculations, and you can run it again. There you go. So yeah, 4.9, 2.45, so a little bit worse. But this current is going to be 2.5, and here's 2.45. Cool. And that'll delete them. If you want to delete a circuit, you have to break the loop and run create while standing on a wire. You have to run create while standing on at least one of the glass blocks, and then it'll go to everything. And to delete it, just again, break the circuit, run create. So yeah, so we build this. How to use this guy, you just break the circuit, run create. It'll create it. It might freak out here. Then you can run solve from anywhere. You don't have to be standing on a block. But yeah, you can run solve and it'll solve things. But it kind of doesn't give you good answers when there's nothing. It says not invertible. So if there was some kind of weirdness with how you designed the circuit, it'll say something like not invertible. I will admit the caveat here. There is a caveat here. It doesn't work in all cases. It doesn't work in all cases like perfectly for a ton of stuff. Like a lot of times if you throw a couple voltage sources at it, it'll freak out. And that's because the matrix inversion method is not perfect. And even I checked it with the MATLAB program, and it even, yeah, the matrix inversion algorithm doesn't like it, because when you have the bigger arrays, the more sparse arrays, you're going to have a lot more zeros involved with the MNA method. And the so when you have a bunch of zeros, that's a lot more likely for this matrix inversion method to freak out and give you the wrong answer. You could probably remedy this with normalization, when you normalize the array before inversion, and then try and denormalize it afterwards. But I didn't want to spend that much time on this because I think the tricks involved with getting the individual elements to work was the fun part for me. Trying to make it work better is not fun for me and not really worth my time. Anyways, if you guys thought this was cool, leave a like. Let me know what else you want to see. I'm sure only like 5 of you are going to watch this video and like 1 of you are going to watch the whole thing. But if you made it to the end, good for you. If you understand things that I was saying, good, even better. A lot of times it's hard for me to understand it. But anyways, thanks for watching, and see you in the next time. Maybe the next post like this is going to be something with machine learning, but you'll just have to wait and see. So, see ya.